Hi everybody, welcome to my 7th torsional bar video. In this video I'm going to be solving the problem you see here. I'm going to be finding and then plotting the internal torque and twist, and I'm also going to find and show you how to find the location and magnitude of the maximum shear stress. If you want to know something else about torsional bars, feel free to check out any of my other torsional bar videos. Alright, so the first thing I want to say is just when you see a torsional bar problem, immediately compare it to the knowledge you already have on axial bars. So I'm assuming if you're in a torsional bar section, that's usually done after the axial bar section in your course. So I'm going to make as much comparison to that as I can. So the first thing we'll do is plot the internal torque. The internal torque, that's an internal reaction. The way we expose internal reactions is by making a cut. So let's do that here as well. Let's make a cut a distance x away. Let's call this distance x, and we'll make the corresponding cut right here. And we'll look this way. It eliminates the need for us to define the reaction at the support later on. Alright, so now let's get a free body diagram happening of this piece. Alright, so there we have it, that bit of a free body diagram. Now as you can see, this applied torque is applied as a constant over the whole bar, so we're going to have to do something about that because it's varying, or not varying, but the internal torque is going to be changing as some function of x. So in order to find the magnitude of this applied torque over this piece, we need to replace this, if you will, a system of applied torque with a single point torque. Alright, it doesn't matter the location in this question, we just need to replace this applied torque with a singular torque. Alright, now we know that this is constant, so this would be like a certain amount of newtons per meter, and we times that by a certain number of meters, that's going to give us the total number of newton meters. Alright, so it's just like similar to newtons per meter times meters when we had axial bars. So I'm going to redraw this free body diagram and replace it with an equivalent force. That's the result of timesing this applied bit with this length. We'll figure out what that length is in a second. Alright, so there we have it. I've replaced this by just a single torque. Now what is the magnitude of that? Well, like we just said before, since it's a constant, we just do that constant times the length. Now, when we're going to eventually plot this, we want to plot it the way we're normally used to plotting things. That is, the x starting at the origin and then getting bigger as it goes out. So in this case, we could call this length x, but then we'd have to plot our system in reverse, and that could get complicated. So what I like to do is take my origin as being x, and taking our cut at a distance x, and that's going to be this dimension here. And if the overall length is L, that means the section left over, that length is going to be L minus x. Alright, so the amount of torque here is this times the length, so it's simply going to be T naught L minus x. Alright, and then summing up the forces. Wait, it's not the forces, but I said that because I'm so used to doing that. That's actually a good sign. The sum of the torques in the x direction need to be 0. Alright, and of course this is still called T. And T is of course equal to that, which is write that straight away. L minus x. Alright, we can write this actually as a function of x, because it's not defined for any particular point. Alright, so let's go ahead and plot this. Okay, so this is the function that describes the internal torque as a function of distance. So we just gotta kind of look at the boundaries and then solve for the boundaries, and then later on we'll plot what it is in between. So when x is 0, it's just t naught L. Alright, that's the value we'll give to the function as it's at 0, somewhere up here. When x is equal to L, this whole thing becomes 0 here. And in between, it varies just linearly because x is to 1 power. And it's minus x, and that's going to be a negative. If you take the derivative, you find that to be negative. Alright, so the slope is negative. Simply just connect those two. Okay, so there's the distribution of the internal torque. Now let's move along to finding the twist. Okay, and just like we found displacement when we did axial bars, we do it the same way when we find, phi or the twist, because phi and delta are, the equivalents of each other, just they're in different worlds, if you will. And we use this equation, d phi Alright, so this equation allows us to calculate phi if any of these things are changing. In our case, g, that's the material property, it's constant, and j is also constant because we're told it has a diameter d. Note here that we need to express phi in terms of just d, t naught, and L. Alright, we shouldn't have any other terms in there. So phi as a function of x, I'm going to call it that because I'm not going to evaluate the integral explicitly. I'm just going to do the integral without putting in any limits. It's equal to the integral, the normal force. Now, see, there we go again. I'm mixing up axial bars. It's not normal force, it's its equivalent. Alright? Slip that in there, see if you're awake. Alright, so t is a function of x, that's this. dx over gj. Now we don't know what j is yet, but we know it's going to be constant, so let's just keep it in here. Alright, we can go through and integrate this, and we're going to get this. Okay, and this equation describes our twist as a function of any sort of x. Alright, so this makes it easy for us to plot it if we just have a function. So let's go ahead and plot the twist. Okay, so when x equals 0, the whole thing is 0. Okay, so that goes right here. When x equals L, or at the very end, what does it equal? Well, let's just plug in L here. That becomes t naught L squared. Put an L here. L here becomes the same thing, but divided by 2. So factoring out the t naught L squared, 1 minus half, that's a half. So phi at L is just simply t naught L squared over 2gj. Alright, now this isn't an explicit answer because we haven't expressed j in terms of the variables we know. Alright, but we know that for any circular cross-section, j is alright, so we take this, we plug it back in here, and we're just going to resolve that. Okay, so this gives us the value at the very end. So we can label that point right over here, give it the value 16 t naught squared. And how about the line connecting them? Well, it's x squared, that's a quadratic, and that's a negative x squared, so that's going to be concave down. So let's plot that in there. Alright, there we go. So only one step left. Alright, and this is usually like, you know, a part B of a question that you'll get in class. And it is, find the location and magnitude of the maximum shear stress. So we know that shear stress is given by this equation here. Tau is torque times radius by J, the polar moment of inertia. So that means T max is when T is maxed, right, and R is maxed. So this is going to be the very outer radius over J. Alright, and J is maxed pretty well always because we're just always taking the overall moment of inertia of the whole piece. Alright, so T max. We can find T max by looking at this equation here. Let me just copy that down. Alright, there we go. Okay, so let's just look at this. We don't need to take any derivatives to find when it's maximum. If x equals L at 0, if x equals 0, hey, that's T not L. Alright, and we can just look at this graph here. When is it maximum? When it's right at the base. Alright, so T max is just simply T not L. Alright, and R max we know is D by 2. And we still know that J is pi by 32, D to the 4. So we take all these, plug it back into here, and the final expression then for shear stress, the maximum, is right? And the location, well, we already actually described this, or found this. It was when x equals 0. So at x equals 0 meters. Okay? Alright, so that brings us to the end of this video. I hope that helped you out. If you ever get confused with these sort of torsional bar problems, just always think back, what would I do in the axial world? Alright, we'll see you in my next torsional bar video.